Parameters and its significance. So first one, modulus of rigidity, that is G. It is a measure of shearing stress which produced shear strain. The ratio of shear stress to shear strain is the ability of material to resist shear deformation and shear modulus of metals decreases with increasing temperature. Shear modulus increases with pressure. It is denoted by G, capital G, and the unit is Newton per mm square or GPa. So modulus of rigidity, capital G, is nothing but ratio of shear stress to shear strain. It is tau upon pi psi. So it is a measure of shearing stress which is produced to shear strain is modulus of rigidity. It has the ability to resist shear deformation or twisting. Second one, polar moment of inertia, that is Jp or J, denoted as Jp or J. It is the quantity used to predict an object's ability to resist torsion, just like I beam is used in beams, just like the moment of inertia I used in beams for deflection. It is given by Jp or J. Unit is mm raised to 4 or meter raised to 4. Polar moment of inertia is used to analyze non-circular cross sections, that is polar moment of inertia for solid and hollow shaft is given by the formula J equals to pi by 32 d raised to 4 for solid shaft, J equals to pi by 32 d raised to 4 minus di raised to 4 for hollow shaft. Next, third one, polar section modulus, that is Zp. It is a ratio of polar moment of inertia to the radius of shaft. It is denoted by Zp. Zp is Jp by R. R is radius of the shaft. So pi by 32 d raised to 4 upon d by 2. We get pi by 16 d cube for solid shaft. Gp by R is pi by 32 d raised to 4 minus di raised to 4 whole upon d by 2. You get pi by 16 d raised to 4 minus di raised to 4 whole upon do. This is for hollow shaft. More the polar section modulus, lesser will be the shear stress produced. More the shear polar modulus, less will be the chances of failure of the shaft. So this was about the polar section modulus Zp. Fourth one, torsional stiffness K. It is defined as torque applied per unit radian twist. So it is defined as torque applied per unit radian twist. So K is given as torque by the angle of twist, so T by theta, or it is equals to or tau by R by the torsional equation, or G theta by L. Fifth one, shear stress, that is tau when a shaft is subjected to torsion. Shear stress are developed. It is denoted by tau. Unit is Newton per m square or MPa. Shear stress in a circular shaft varies directly as the distance r from the axis of shafts. Maximum shear stress occurs at outermost fiber at radius r, and zero shear stress occurs at center. Material like wood is weaker in shear longitudinally than transversely. The fibers will crack open in axial and longitudinal direction. The material which is weaker in transverse shear, like cast iron or chalk piece, a crack along helix inclined at 45 degrees to the axis of shafts occurs. So sixth one, power transmitted by shaft. In practical application, the diameter of the shaft has to be determined depending on the power to be transmitted. This can be calculated by the formula P equals to T torsion into omega, angular velocity omega. So T into omega, or nothing but omega is nothing but T into 2 pi n by 60 watts. If terms of kilowatts, so it's 2 pi n by 60,000 kilowatts. Seventh one, torsional rigidity. Torsional rigidity is the torque required to produce a unit twist in unit length, also known as torsional stiffness. So torsional rigidity theta is TL upon Jp. So parameters and significance. First is modulus of rigidity. It gives a measure of shear stress and shear strain produced, and this ability of material resist shear deformation, and this decreases with increasing temperature or increasing pressure also. Second one, polar moment of inertia J. It predicts the object's ability to resist torsion. So polar moment of inertia is measured in mm raised to 4 or meter raised to 4. You can formula is G by 32 D raised to 4 and G by 32 D raised to 4 D raised to 4. Hollow shaft. Next, polar moment of inertia. It is the ratio of polar moment of inertia to radius of shaft. Z equals to G by R. So more the polar moment is, lesser will be the shear stress produced. More the polar moment of polar modulus, less will be the chance of failure of the shaft. Torsional stiffness, it is defined as the torque applied per unit twist, that is K equals to T by theta, tau by R, G theta by L. Shear stress, shaft subject to torsion shear stress are developed. Shear stress in circular shaft varies directly distance R from the axis of shaft. So it is maximum at the outer radius, that is R, and zero at the center. Material like wood is very weak in shear longitudinally than transversely. The forces crack open in axial and longitudinal directions. The material which is weaker in transverse shear are cast iron, chalk piece. They crack along helix at an inclined angle of 45 degrees. Next is the power transmitted. Power transmitted shaft. The diameter of shaft is determined depending on power transmitted. This can be calculated by formula P equals to T into omega, T into 2 pi by 60 or T 2 pi by 60,000 kilowatts. And torsional rigidity, torque required to produce unit twist in unit length. So torsional stiffness theta equals to TGJ upon jp.